but I've not seen it go live. Okay, so now I'm live, I guess. Good. So this seems to be something or other going on right now. It's showing up over there, so the world is good. Current viewer is 1, and that viewer is me, so I could check it out. So let's just see what's going on. So this does show my face, I think. Look there. Now it's showing all this stuff. So I think I told it to look at only the window. Oop, I don't want to see that. Okay, so does that go black over there? No, it's not going black. Alright, so let's just move things around. Okay, now that goes black. And you're seeing this, okay. So you can't see my stuff. Let's see. And so I come up here. So what am I doing? Well, so one of the things I've been doing for the past month and a half, 2 months or so, has been I've been tweeting these short papers, right, here and there. I don't know who any of those people are. Why I don't really know about them. I've been tweeting these short papers, right, and I'm just reading one of these short papers per day. They're again completely short, very short papers, so it's nothing strange about that. So each one of these papers, more or less, I read, I tweet, I do a one-sentence synopsis as best I can after having read it once, and all those things. Let's see, here is the first one, right? So I've got The Electrostatic Vacuum by Mathur, I think. The Bounce of Nothing by Draper, Garcia, and Lillard. And does the Hubble tension signal a breakdown of the FLRW cosmology by Krishnan, Mohayaee, Colgáin, Sheikh-Jabbari, and Eoin. So lots of people in that one. So I went through and I've just read those, and then I read them again. I read them last week, tweeted which ones I read with a little synopsis, and now I'm going to come back and I'm actually going to look at each one individually and talk a little bit about them. Okay, so that's more or less where I'm going to go with this, is just talk about those. If you have questions or something, go ahead and leave me questions. If you want to talk about anything, I can talk about just about anything, except things I don't know about, which are a lot of things. But if you want to talk about something, that'd be awesome. So here I am. So we want to look at The Elastic Vacuum by Mathur. So what does that look like? I'll click over here to the PDF, and we'll just play with the PDF like we did last time. Seems reasonably good. Let's see. So this was, you probably can't see it. Where's the control? This was an essay with the Gravity Research Foundation for awards on, for awards on gravitation. There are places like this around that will give these essay contests and give little grants and things like that. So FXQI is another one that's a fairly interesting one for foundational questions. You see that Mathur is including a lot of his own papers in here, and so he's sort of talking about a lot of things he's been thinking about for about 20 years at least, right, based on the dates in this paper. So what we want to talk about is this elastic vacuum. So what is going on with the elastic vacuum, the way he's going to talk about it. Well, basically what he's saying is that there's going to be a vacuum energy due to thermal fluctuations. All right, and so what he's going to do is he's going to come through and he's going to talk about how you get that in string theory. So he's building up these fuzzballs, right? And a fuzzball is basically what happens to strings inside of a black hole. So if you get inside of a black hole, according to this, bad things happen to your compactified dimensions. So there's some pinching in your compactified dimensions, right? For string theory, superstring theory, you've got 10 dimensions, right? 3 of space, 1 of time, and 6 of who knows what. They probably have some idea about what, but I'd have to look at how they measure those things. Actually, we will look at something pretty soon about them as well. It's really, really interesting. But here, what we're looking at is we're saying, okay, these compactified dimensions, you might say, I guess the normal way to say that is that the compactified dimensions are like little circles. So you have 6 little circles, or maybe a 6-dimensional sphere, or maybe 2 3-dimensional spheres, or something like that have been compactified. It's not really right, but it's close enough, right? You get the sort of idea. You're rolling up these really tiny dimensions. And normally, those are perpendicular to our normal 3 spatial dimensions and 1 time dimension, right? Trivially tensor is what they really need to say, not necessarily perpendicular. So, what's happening here with with this fuzzball is that when you get these this pinching inside of the black hole, inside of the event horizon of the black hole, excuse me, you get this pinching of the compactified dimensions, and that's going to create monopoles, and those monopoles are connected by topological spheres. And you're basically creating strings inside of your black hole. Okay? And these strings, these branes, short for membranes, sort of 2-dimensional strings, those are going to be those are created inside that black hole. And he's talking here about how there's no information paradox because these fuzzballs can radiate information out normally, so you don't end up with an information paradox like you do in general relativity when you're talking about black holes. So we end up here with our fuzzball. This is his Mathur's schematic of a fuzzball, right? And basically what he's doing is you can tell he's a physicist, because what he's done is he said, well, each one of these little strings or branes, represented by these black dots, these are just masses, and they're connected by these topological spheres, which he's decided are these long gray things, and those connections are basically springs, right? So you have a spring here and a spring there, right? And so they vibrate and they have energy and all sorts of things like that. And this is his model of the fuzzball. He says, okay, now this fuzzball exists, or if it exists, it has some energy and it vibrates because it's got that energy. Fine. That's really just the fuzzball. That's just the fuzzball. We haven't really gotten to what he's talking about in terms of the vacuum energy. He wants to do something with these little fuzzballs and make vacuum energy out of it. What he's thinking is that these things, these fuzzballs, if they exist, have to have some random probability to exist even in the vacuum, so that just randomly they would pop up out of nowhere, right? So you end up with what he's calling these virtual fluctuations of fuzzballs. Actually, he's calling them vecros, virtual extended compression resistant objects. Where does he say that? It's awful. Thus, the virtual fluctuations of the black hole microstates form an important component of the gravitational vacuum for all masses. we call those fluctuations vecros, virtual extended compression resistant objects. So I'm not sure exactly how long it took him to come up with the acronym. That's probably the most difficult part of this whole thing. And so basically he's saying here, he's calculating, or he's giving, it's not really calculating in this paper because it's really just an essay. He's giving some ideas about the number of states here for each one of the possible energy levels based on the mass of the vecro, and the probability of there being this virtual fuzzball, this virtual black hole. That fuzzball is a black hole in string terms. This virtual black hole to show up right here, with A being proportional to this and this being proportional to that, and so forth and so on. So you have some probability for these fuzzballs to occur. You have a large number density, and so these become an important component of the vacuum, of the gravitational vacuum for any mass at all. So that's basically what he's saying is, okay, so this thing is going to give me some component of the vacuum energy. This is going to give me some component of the cosmological constant. All right. So this is just sort of what he's doing here. Here's his little depiction of it. So you see this depiction on the left, that's sort of your matter collapsing into a black hole. And here you can see that this spot right here is your event horizon. Right. So the event horizon, this is where the light cone has turned 45 degrees. So one axis of that light cone is basically pointing straight up at event horizon, and any other possible future you have is going towards the center of the black hole. So unless you're light that's pointing in the exact right direction, you're going to the center of that black hole. And this continues, right? So when you're on the inside of the black hole, your light cones are tilted more than 45 degrees. That means your time-like direction is going this way, all right? Or at least as far as your metric is concerned. I'm not sure if there's any reason to believe that time actually proceeds the way, time proceeds in normal life in that direction. But I can't think of any better explanation of what it would do in that particular state. But, there might still not be possible for that to actually happen, but I'm not sure. We come over to the right-hand side. This is the fuzzball picture. So you see the fuzzball is collapsing, right? And we get to the point where the fuzzball, or we get to the point where the event horizon forms here, and then the fuzzball, because of all the quantum mechanical stuff, basically fills up the entire event horizon. So we no longer have this singularity at the center as all of the mass compacts towards the center. You basically end up with a fairly even distribution of energy in this big, giant, entangled mass of strings and brains and little topological spheres, and we don't really know what they are. So that's our fuzzball on the inside there. So that's the collapse, and why he likes the fuzzballs. Do we have a... I probably don't have another picture here, do we? No, we don't have another picture. But we have lots of equations. And equations are pictures just in another form. And so he talks a little bit after that about what's going on. Now, the important thing here is that he starts to look at these fluctuations and try to figure out what the cutoff for the size of those vecros are. And here he's put that in terms of the horizon radius h to the minus 1 over h. And so he's looking at the two phases of the universe. One is basically the radiation phase. It's the early universe. Before now, this is when the universe is No, I guess it's still expanding, but when the universe is expanding and creating everything. At this point, he says, because this exponent, this is going to be an exponent, kt is equal to e. Kt is equal to e to the minus this thing, or something like that. So I wrote that down somewhere around here, but I'm not seeing it in front of me. It's probably okay. Kt is proportional to minus this alpha. So Kt being the Boltzmann constant times the temperature. That's basically like the energy density, right? So that's so the energy density this is more or less the energy density of the universe at a particular time. For the radiation phase, that's 1/2, and you basically end up with this saying that you have no vectors larger than the cosmological horizon, and therefore they don't do anything with the vacuum energy. They're not pushing the universe out. But right, what happens is when you get to the dust phase, our phase, the phase with lots and lots of matter, you have the size of this vector being larger, twice as larger than the size of the horizon. So it's pushing the universe out, right? It's pushing the universe out with this creation of strings and brains, and so yeah, that's pretty much it. That's what's causing the dark energy in this model, based on the fuzzballs. Right? So yeah, actually that's still here, right? So if we say this is the size of the universe and we have this thing, it's just a little bit bigger, pushing it out. That's what's causing the the vacuum energy that's causing the cosmological constant. That is the first, number one, of those papers. Got anything to say? All right, so let's see. What is the second one? The bounce of nothing. Okay, the bounce of nothing. This is a little bit different. It's still a string theory paper. So this is another string theory paper. And it starts off talking about creating these bounces. So there are, in quantum gravity, you have bounce solutions rather than a Big Bang. Actually, that's not what this is. This is about another thing. All right, so you have a false vacuum. Let me see if we have. I don't think we have the right picture here. No, we don't have the right picture here. So we don't really have the right picture here to talk about it. But so Edward Witten found something interesting. Right, he found that there's sort of an instability in the Kaluza-Klein vacuum. Right, so that when you have this false vacuum, That's basically what happens in particle physics. Is that there's a false vacuum, which is E equals 0, but there's some actual smaller number, a negative energy, which is sort of the real vacuum where nothing is actually happening. I think that's the way it is. Maybe it's reversed. That's the way I think I just read it. So there's a chance when you're in that sort of situation that there'll be some tunneling. Right? There'll be between vacuum solutions, and when that happens, well, there's a probability that the universe will decay from this false vacuum into the real vacuum, which is the negative solution, which would possibly have problems for us, give us some problems. It's probably a pretty low probability. We're probably not going to disappear into nothing for no reason, but that's what's going on here. This is basically for a de Sitter universe. That's sort of the universe that we should have with a positive cosmological constant. And it's really hard to get solutions from string theory there. So Bounds of Nothing, another string theory paper. In fact, there are conjectures here that, you can't have a de Sitter solution like we think we have for us. Actually, we'll talk about that more in the next paper after this one. And possibly they're just metastable. And so we're looking at the metastable idea here, I think, is how I see it. And more or less, what you and I are doing is we're living in this metastable universe with the false vacuum, right? And there's a chance that at some point something will happen, and we'll fall down into the false vacuum. You probably remember something in high school where you had, super saturated salt in water, right? Where you took some hot water and you put as much salt into it as you could, dissolve as much salt as you could into the hot water, let it cool down, and then it looked like just normal water, and then you tapped the glass of water, right? Just tapped it, bang, and then the water just precipitated, or the salt precipitated out of the water. You might remember that. So our universe is like that hot water that's cooled, right? And we're just waiting for somebody to come along and tap the universe, and then the salt will all precipitate out of the universe. Maybe not the salt, but something will happen. We'll go back down to that lower vacuum, in whatever way that means, right? You'll notice they're looking at a 5-dimensional toy model. This is a de Sitter space, and the de Sitter space is really like an embedding of a 4-dimensional object in a 5-dimensional space. I think with 4 spatial dimensions and 1 time dimension. I think anti-de Sitter is 2 time dimensions and 3 spatial dimensions. So that's both 5. But de Sitter and anti-de Sitter, I think that there's a sign difference there in these hyperboloid solutions. So we're looking at sort of a 5-dimensional model of the universe that would fit a de Sitter space, right? I'm not sure if that's why, but if not, that's a coincidence, right? So that's where we're looking. That's what we're looking at here. So what are we looking at here? So the idea is, so we have this potential for a bounce, right, from one of these solutions to the other, and that's bad. There's another idea that someone else had, Ed Witten, a well-known physicist, and he had this idea of a bubble, which is an instability in a Colgáin vacuum. Colgáin is a 5-dimensional theory where you have one compact to 5 dimension, rather than, as we were talking about before, the 10 for superstring theory. It's a much older one and was trying to solve another problem, but a lot of the techniques for the Colgáin solution, or Colgáin equation, I'm not sure exactly how to say that, are still used, right? So what happens in this bubble that Witten put together using Colgáin vacuum is that you have the false vacuum decaying into the true vacuum. Or actually, I think for him it didn't have to be there. But they're going to extend this to the true vacuum here, So what would happen is you have extra energy in that Colgáin thing, and it'll decay, right? And when it decays, it turns into a almost identical de Sitter space, almost the same as the original de Sitter space, except just take a little bubble out of it. Just take a tiny little bubble of nothing, not a vacuum, nothing. So when physicists are talking about a vacuum, they're sort of talking about the structure of space-time in some way, of the things that are the thing that makes up this structure of space-time. There's just nothing in there, right? There's just nothing in that bubble, all right? And it's just an empty little bubble, and that fifth dimension is important because the shell of that bubble is in the fifth dimension, not in the other four. So that lets it be a nice stable bubble. And so the idea here for this paper is that when they look at this, they think that the bubble is going to beget a bounce, is going to beget the false vacuum. All right. And that's more or less what they've done. I think, let's see. So, lots and lots of work in here. Very interesting number, right? Showing here that for a class of potentials, so this is the scalar potential, and that's the that's basically the thing that's going to parameterize these spaces. Get this energy over here, which is basically proportional to the exponential of some number times that potential scaled by the Planck length, and that number has to be greater than -6. If that number is positive, you have a nice stable de Sitter space. If it's between -6 and 0, not necessarily so. And so this figure 2 is showing basically what the possibilities are here. So here you've got your minus the square root of 6 over here. And you have your minimum here at phi equals 0. That would have, my guess there is you basically have no false vacuum in this case. And then you have some more differences out here. And so we're looking in here, in this particular situation is where something interesting happens. Right? And basically, if they look at this, if you're on this side, there's no minimum size to that compactified dimension. When they look over here, however, there's a minimum size to your compactified dimension. All right? Which is really interesting. So this is basically saying, we talked about these compactified dimensions in string theory, right? These little curled up dimensions that aren't really dimensions, that aren't things you can move around in freely. And normally, they're just assumed to be small, right? Maybe they're at the order of the Planck length, right? Something like that. And in this paper, basically, after finding the probability of universal decay, so there's a probability that the universe will dissipate. It's like e to the minus 560, so you don't have to worry. Then there's a minimum, right? So right there, in the insert, there's a minimum where you figure out what that size of the universe, or that minimum size for the compact dimension is. And it's right here. This leads to a moderate lower bound on the size of the compact dimension. R is greater than or about equal to 8 inverse Planck lengths. And I'm just going to assume that an inverse Planck length is a Planck, or inverse Planck mass. I'm going to assume an inverse Planck mass is a Planck length. I tried to play around with it because I don't really know what the how they do this in astroparticle physics or high energy physics. But, I played around with the math, and it looked like it was about one, dimensionally, it probably should end up being one Planck length. So, there you have it. You have the lower bound on the size of those compact dimensions, and it's pretty small, right? It's not like 5 meters or something like that, which would be surprising because then we should be able to see them, right? What actually things are doing in those compact dimensions, I don't know. Trying to think if there's some way to push this into dark energy or something interesting, but I can't see that right now. So there we go. That's number 2, a minimum size for the compact dimensions from this balance of nothing by trying to reconcile de Sitter space with string theory. But of course, we're going to have another problem. Right? Here we have Krishnan, Mohayaee, Colgáin, Sheikh-Jabbari, and Eoin. Does the Hubble tension signal a breakdown in the Friedman, Mathur, Robertson, Walker cosmology? I gave too many. I pronounced too much stuff in the Math. Wait. And this is interesting. Basically, what they're trying to do is they're trying to look at this difference between the ways that you can measure the Hubble constant. And we'll talk about that a little bit on Physics Frontiers in about a month and a half. There should be one coming out. What days? So about in a week and a half, I'll put out probably one on the Higgs portal, and then we'll do the Hubble constant after that. So we'll talk about the Higgs particle and dark energy on the next Physics Frontiers, and then after that we'll talk about the Hubble tension. Those are already recorded, and we'll be talking about dark stars, which has something to do with the first one actually. The first one of these papers in person next month. That's just going to be me and Randy talking. Okay, so here you're looking at that tension. We have a lot of problems because we've got two different kinds of measurements. Right? We have two measurements of what's going on with the Hubble constant, right? We've got those that are based on supernovae, right, and other sort of historical data like that, and that's telling us one thing, and then we have another set that is basically the Planck experiment, the thing that's coming from observations of lambda cold dark matter. This stuff, they're giving us two different measurements. Here he's saying 73 kilometers per second per megaparsec versus 67 kilometers per second per megaparsec. Actually, that was the first one that used those numbers. What he's going to do here is he's going to try to reconcile the all of this with the Friedman, the Mott, Robertson, Lemaitre, I have no idea how to pronounce that, Robertson-Walker metric, FLRW metric. Now, this FLRW metric, you might say, well, who cares about that? I've never heard about that. You just told me there's this de Sitter space, there's this anti-de Sitter space. I've heard about that in Minkowski space. What is this FLRW metric? Well, the FLRW metric is basically any sort of conformally flat space, right? It's a conformally flat space. It includes your de Sitter space. It includes your anti-de Sitter space. It includes your Minkowski space. They're all sort of wrapped up in the FLRW metric. And this is basically the standard metric for cosmology. It's the one that gives you this idea that there was a big bang and stuff like that. So the problem here is that we're not really getting what's happening. This Hubble tension that I was just talking to you about here, well, according to this quintessence, it's basically gotten rid of quintessence. It's bad even for a minimally coupled scalar field for lambda, for the cosmological constant. It's that bad. If this Hubble constant problem is something real, and not just some weird thing to do with the measurements, then it's really screwing up a lot of cosmologists. Okay, if it's true. Do I know? I do not know. This is what he tells me. Actually, he's going to say, and he's got a reference saying there's actually another reason for that came out this year. It's a 2021 paper, and so probably it's not an FLRW metric, right? It's some other kind of metric coming out there, and I'm not sure what it is. Actually, he doesn't tell me what it is. He just says there's a problem here. Okay, so what he says is that, okay, we've got this problem, right? And we don't know what that problem is. This Hubble tension is challenging for late-time dark energy. How are we going to fix this? And, right, because the basic ideas that people usually use for cosmology aren't working. They're not working with this Hubble tension. So, what are we going to do? We have a whole bunch of data, and in a way it's not consistent. Well, the proposal here is that this FLRW is just not a acceptable spacetime. All right. And we've got all the stuff from the sneezes and stuff like that. And basically he's coming through here, and he's using big equations to scare you off, because that's the whole reason why we do that in physics. I know. I've read my student evaluations. Big equations are for scaring people. Let's see. So these are some of the things. So, for example, we're going to assume now that we're going to assume several things from several different data sets, and see how they work out, right? That the age of the universe is 13.5 billion years. That's the most up-to-date measurement idea about what it is. That the highest redshift, I think that's high, is 1.141. That's a frequency shift because of how fast things are accelerating away. There's an absolute magnitude from shoes here is minus 19.2, and of course I clicked on the reference. And then there's this sound horizon. Oh, there it is. Why didn't I see that? It's 14 or 147 megaparsecs. All right. When I wrote this down, I had no idea what the units were, and I had the paper sitting in front of me. So where are the units? Well, I just didn't see them. All right. So, oh, I see. Okay. So it's right here. I was taking the data from here, right? And here he does not have the units. Here he has the units. So this is where I was looking when I was writing down the data. Ooh, naughty, 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 naughty. Shame, shame, shame. Alright, so somebody write them and tell them that they have to fix their units. Alright, otherwise they're going to lose 2 points on the test. Let's see what's going on here. Then they do a lot of calculations, and I think the big problem here is that they find, or not the big problem, but the thing that they see, the thing they say they see, right, is that we don't see something that works correctly. That the RD that they're going to use for this fit, if they let RD be a free parameter, then it's going to end up far off from that 147. It's going to be at this 141, and that's an issue, right? That's a big issue, or that's a reasonably big issue. That means that they have a maximum Hubble constant right there, this 71 kilometers per second per megaparsec. Right? But that Planck data said it was 73, right? So if the data is correct, then we're in trouble. Here, basically what we're seeing is their fits. So if they're using this red circle here is what they get if they're using RD prior, which is if they're measuring that, if they're using that shoes data for that sound horizon, then this is the range of H0 and RD that you can get. So this is your Hubble constant here. And here's the Planck data, and here's the shoes data here. So this is your Hubble constant if you choose that. If you're fitting the Hubble, if you're fitting RD, if you're letting RD vary. And up over here. And basically what should happen is that what you would like is you have some measurements here around 67, you have some measurements here from 72 to 74, around 73, and you'd like the possible values to overlap both of these, right? So these are your measurements, and these are your fits. They should fit. And so there's a little bit of tension here. Actually here there's not a lot of tension. Where did we put it here? So it's only 1.2 sigma difference. So that's not too horrible, right? But that's still just the maximum, right? So, and so, you know, there's a lot of other experiments coming up, right? ACT, SBT3G, Simmons Observatory, and CMB S4. And you can, you know, look these up if you want. There are references in the paper. And there's a link to the paper right down there. But if you come over here, there's a problem with some quasar data that's 4.9 sigma significance, a 4.9 sigma discrepancy. So if you have that kind of discrepancy, then there is a problem. There could be a problem with that FLRW thing. So at some point I might want to look at this 88 here. No, that's too. For some reason I thought that was 2021. This is 2020. I mean, it's like September 2020, but still it's 2020. Old data now. Old data now. Okay, so there's that last one there. Is there a problem with this FLRW cosmology? And if there is, then that gets rid of all the easy ones. It gets rid of all of the easy solutions to general relativity. So going over those, we had the elastic vacuum that said that there was some reason for this expansion of space-time. We have bounce of nothing, so we have these said that there were these fluctuations in black holes. These virtual black holes get created in space because of string theory stuff, and that causes your lambda, which is the cosmological constant. That gives you your vacuum energy. The bounce of nothing, which says that if you have a false vacuum, then you can have these little holes in space showing up, and the sizes that you get for those holes in space, or basically what happens with those holes in space, will limit the size of the compactified dimensions of string theory. So that's interesting as well. We said that was about 8 Planck lengths, so that's pretty nice. And then we have this Hubble tension, and that Hubble tension seems to be one of at least 2 or 3 different problems with the Friedman, Lemaitre, Robertson, Walker cosmology metric thing. It doesn't work anymore, so that's not the one we should be using for cosmology. So those are the things that I've got there. So let's see. Okay, so, oh, there it went. It did it. Okay. All right, so now I know that. Okay, so just a couple things. So if you like those things I talked about, what are those book reviews? I just happened to be looking at this guy, right? So you can look forward to one of these. Exact Spacetimes in General Relativity by Griffiths and Podolsky. That has a lot of information about these metrics. Right, so let me. Yeah, so there's some goodies about the FLRW metric right there. So this is a very interesting book, and I'll talk a lot about that whenever I get done with it. Right. It basically has a whole bunch of different metrics, and one metric a week. I might be done with this by the end of the year. Also, coming up in about a week and a half, we have the Higgs portal episode on Physics Frontiers, and there's my show art for it. And you only get that if you're a Patreon subscriber at an absurdly high level. But that's the only thing you get for the absurdly high level. I just figured if I was going to do something like that, I was going to do that. So, those things are coming up. I don't see anybody talking, so if nobody's talking, I'm not going to answer any questions. What time is it? It is. I've been talking for an hour. I talk too much. I talk way too much for somebody who has no friends. So, but thanks for coming by, and I'll probably be back next week. You go by the Twitter thing. Let's go back to the window capture. Go to the Twitter thing, and oops, this guy's too big. Here, and I will tell you each time one of these things comes out. The reason why I've been doing that is just to make myself read these things. Let's see. We'll also say when I've just uploaded a new Physics Frontiers. So if you want to see when I upload to Physics Frontiers. That's one way to do it. I usually post. Where do I post that I've done this? I usually post that the new episode is up on Patreon, on the Twitter, and on Reddit. So those are the 3 places I do that now. I used to do them on. I don't even remember what the thing was called anymore, but it doesn't exist anymore, so I don't do it there anymore. So obviously, if you subscribe, you'll get it anyway, so you don't have to worry too terribly much about it. If you have any comments or questions, go wherever you'd like to go to find them, and I'll talk to you in the future if you're willing to come by. So, bye now.